Okay, so we're going to cover section 13.1. There's no calculus. I don't think there's any calculus in this section. This is vector valued functions. Okay, and we've already done one. That was these have vector output. It doesn't matter what the input is. It's just that they have to evaluate to a vector. Now, in this chapter, the input is going to be a time input. So basically, we're going to say at this moment in time, you're at this position vector. So, and that gives X, Y, and Z coordinates for that vector. But then you can also do at this position, at this moment in time, you're going to have this velocity or this acceleration vector. And those are all functions of one independent variable, which is time. Later on, you'll be inputting a position in space, which is a position vector, and then outputting a vector for some field. Those are vector valued as well. Like a gravitational vector takes a position as an input and outputs an acceleration vector, but not as a function of time. Okay, so those are vector valued as well, but we don't study those till chapter 16. Okay, and we'll be doing, it's basically you're going to have a 3-variable input and a 3-variable output, or I should say a 3-dimensional vector output. So those are interesting, super cool stuff, very physics oriented. Okay, so let's go ahead and jump in here. So the definition of a vector function or a vector value function. Is just that it has a vector output. I think I already wrote that. In chapter 13, the input will be time. I'll say usually, but the input is t for time. And output is r of t, position. It could be v of t. Could we gotta mute someone here. And I'm trying to put it out. Okay, we got it. Okay, v of t for velocity. A of t for acceleration. Now, we'll also talk about forces. But those are the primary vector functions. There will also be a unit tangent and a unit normal and a unit binormal. There's more. Okay, so let's do an example here. R of t equals 1 plus t square over 1 minus t square, comma, t to the third plus t over 2t to the third minus 1, comma, 1 minus e to the negative 2t over t. There you go. One-dimensional input, 3-dimensional output. Okay, so for domain, you have to take all 3 components into account. Okay, so for 1 plus t square over 1 minus t square, we could call that x, okay? And what we need here is that 1 minus t square is not 0, right? So right off, we know that t is not plus or minus 1. Okay, any questions? With the y component, we know that same thing too, t to the third minus 1 can't be 0. So you do the math and t can't be, I think it's the cube root of a half, right? And you can clean that up if you want. Z is 1 minus e to the negative 2t over t. So easy enough, t can't be 0. Okay, so the domain, if I had to do this in interval notation, I might have to figure out what the cube root of t is. So, but I'll just show you on a number line. So, so we know we can't have negative 1. 0 is out. Then negative 1 is here, or sorry, positive 1 is there. And then this is the cube root of a half. And then of course 2 is up here. So the domain would just be some horrible thing, negative infinity to negative 1, union negative 1 to 0, union 0 to the cube root of a half. This is ridiculous. I don't know where I came up with this problem. Union cube root of a half. Cube root of a half to 1, union 1 to 2, union 2 to infinity. I've run out of space. Okay. So there are domain questions on here. I guess there is a little calculus here because we have limits. Okay, so limits. Okay, so if I take the limit as t goes to a on, let's just put the vector function here. Let's just say x of t, y of t, and z of t. This is just defined component-wise. So you just do the limit on each component. Okay, so so if I have r of t equal to, let's say, 2t squared minus 1 over 3t squared plus 1. See, I think I'm going to have t go to infinity. So what if I do, is that what I want to do? Nah, let's do a sine of t over t. And let's do e to the t minus 1 over t. Okay, and so we're taking the limit as t goes to 0. Change my mind about infinity, we'll go to 0. Okay, of r of t. And we're just taking limits of each component. Like that. I have two that need L'Hopital's rule. First one is not indeterminate. So the first one is just -1/1. Easy. Second one, you can do L'Hopital's rule. This is a 0 over, these are both 0/0. So this one's a 0/0. This one's a 0/0. So if we use L'Hopital's rule, we would do lim as t goes to 0. Top is cosine t over 1, and then lim as t goes to 0, derivative of the top is just e to the t over the derivative of the bottom, which is 1. Now I think we can just say this is -1, 1, and 1, right? So taking limits on vector functions, yeah, it's a thing. Any questions? So the next part here is we need to be somewhat competent with space curves. These are difficult to draw. So I only have you draw the most basic ones. If they live in a plane, you can draw anything. If they are three-dimensional space curves, then I think I could have you draw a line without feeling guilty. In space, it's not easy, but it could be done. There's a helix, and then of course circles are pretty straightforward. So these are all going to go into the category of space curves. Okay, so basically R of t is a position vector that traces out points on a 3D curve as t varies. Okay, so we've already done lines in space. So I think I'll remind you line, I'm not going to go over this again. Lines, we said R of t equals R naught plus V times t. So R naught is just any point on the line. V is a direction vector. Okay, and this could be R1 minus R0 if you want a formula for V. R1 is a position at time 1. It doesn't matter what time it is. Position 1, R0 is position 2, and 2 points define a line. Maybe I should have said 0.1 and 0.2. That's what I feel like I should have said. 0.0, my bad. 0.1 and 0.0. Okay, and it doesn't matter what the times are. They will be time 0 and time 1, but that's irrelevant right now. Okay. That's how you create a line through 2 points. Any questions about that? We've covered it already. Okay, so then let's do the helix next. This one I expect you to know. Okay, so this is basically, it's a circle in 2 coordinates. So you could have like circle in 2 coordinates. That could be like a cos of, let's say, omega t and b sine omega t. And those, sorry, a sine omega t, my bad. So those will trace out a circle in 2 coordinates, and then a linear function, let's say plus a linear function of t in the 3rd coordinate. Okay, and that'll always trace out a helix. So let me just give you a quick little example of this. Okay, so my R of t is going to be 1 over pi times t, comma, cos t, comma, sine t. Okay, so, obviously y is cos t, z is sine t. That's a circle of radius 1 in the YZ plane. Okay, any questions? Okay, so, need to draw that. But then x is just 1 over pi times t. So this is just x growing at a constant rate. As the point is sort of circling around the x-axis in a circle. Okay, x grows, which makes it look more like a spring than a circle. So this is always a little tricky to draw. I'm going to do my best. I kind of feel like putting a circle of radius 1 down here, although that's not my graph. It's not related to my graph. There, I'm putting it there. For some reason, I just want it. So that maybe that'll help me view this a little better as I go. No fill. Maybe do it in a gray dotted line like that. Okay, so that's my circle in the YZ plane. Okay, and now I'm going to put an x-axis coming out this way. Okay. If I really felt brave, I'd make a bunch of copies of that as I go down the x-axis, because I'm just trying to remember, I'm going round this circle And what I really want are just to create some constant intervals in X. I wonder if I could pull this off here. So 1, 2, 3. I'm going to do one more of those. Too big. Oops. Okay, so what I'm trying to think of is maybe make a table of values. So I'm wondering if I could do the following. So I want to do a full cycle, but I don't really want to go through all the trouble. I think I'm just going to do multiples of pi over 4. So with t equal to 0, then r of t gets to be 0. Cos 0 is 1 and sine 0 is 0. So I would just plot this point right there. Okay, with t equal to pi over 2, then what I'm going to get is 1 over pi. So that's going to give me a half on x. And then cosine of pi over 2 is 0. And sine of pi over 2 is 1. Like that. And then if we do pi, then x is 1 over pi times t. So that's 1 over pi times pi, which is 1. And then cosine pi is -1. And sine of pi is 0. Okay. So what I'm thinking is I was trying to figure out a way where I could kind of just place these circles all over the place. And I don't know if I made that better or worse, but what I meant to do is use those circles to help me figure out where to place my points. So for instance, if I draw vertically up here, right there, I could put a point there. That's where, oops. Right there, that's where t is pi over, that's at pi over 2 right there. No, x, sorry, x is a half there, so that's a half. A half, 0, and 1 on z is what I've got there. Then the next point has x equal to 1. So I'm going to make 1 right here. Y is 0. No. Y is -1. Z is 0. So what I have to do there is from 1, I have to go out this way to the right circle. Let's see if we can make that horizontal, right? To there, maybe. Make sure I got the right circle. 1, 2, 3, yeah. Okay, so here, oops, right here, darn it, having trouble. Right there. Okay, and then the next one would be at 3 pi over 2. So here, x would be just 3 halves. Cosine of 3 pi over 2 is going to be 0. Sine of 3 pi over 2 is going to be -1. Okay, so I'm on the next circle, and my guideline is going to go down, straight down, something like that. And I'll add a point there. Okay, and then on my, and that's a full rotation, by the way, once I get to the next point. So the last one is at 2 pi, where x is going to be 1 over pi times 2 pi, so that's just 2. Y is cosine of 2 pi, which is 1, and z is sine of 2 pi, which is 0. Okay, so 2, 1, 0. So let me put in some more info here. So this is 3 halves, and this is 2. And 2, 1, 0, let me draw my guideline here, is going to go to the left, like this. So I'm going to draw my little last point here. Oops. Right there. And then what I'm going to try and do is draw this. This is basically a spring shape. So I'm going to do my best. Something like that. Okay, that didn't work. I think I'm going to make a real sharp turn and just bend it. There, and there. Technically, these are parabolas. Yeah, that looks terrible. So I'm just going to be real careful as I freehand this. That's fine. And then the next one, I'm going to come out this way. The next one, I'm starting to turn sharper. Like this. Maybe. The last one's real sharp. Like that. And if I had my choice, I'd do a better job on that first one. So I'm going to try a little, just one last attempt here on that first one. Looks better. I feel like that better. Ooh, these are fat lines. Okay, now that doesn't look like anything, but when you put a bunch of them together, it looks like something. So what I need is space. So I'm going to give myself, I'm just going to move things around a little bit and give myself some space and put some of these together. Okay. I think I'm going to just, oops, I'm just going to grab one of these and copy it and clean it up a bit. Okay. So that's just a copy of it. And then I just need to line it up here nicely. Maybe make another, oops, hang on. Okay, so I'll get it. And another. Okay, and it just goes on and on and on. So that's my helix. And I'll enlarge this a bit so that if you look at it in the notes, it'll be a little easier to see. I don't think you need to be this careful. That's the last time I'll draw a helix with such care. Generally, if someone says, you know, if I do R of T equals, if someone says, you know, 2 cos T, oops, 2 cos T, 2 sine T, T, and somebody says, yeah, sketch that, then I'll say, oh, that's a helix in the XYZ plane. So mostly what I'll give you in class, if we get more of these, is I'll say, all right, that's going to be 2 when T is 0, 2, 0, 0 is when so I'm just going to make sure I start at the right place. And this is generally how I'll draw a helix. I'm trying to be sort of careful, but I just freehand these. Okay. And, you know, and here I drew 2 complete revolutions. So here I have 0 less than or equal to T less than or equal to 4 pi, I guess, with 2 revolutions. Okay. And yeah, this is a bit tedious. But I think it should be something you ought to be able to recognize, especially just be able to say, oh, that's a helix. Okay. And then there's a whole load of problems in the book where you're going to look at it and go, I have no idea what that is. We're just going to do our best. Okay. Any questions? What time is it? 7:30. Let's go ahead and take our break. Recording. Okay, so I just wanted to give you guys a chance to see how you graph one of these space curves, like a helix or whatever, in GeoGebra. So again, I usually search GeoGebra 3D, GeoGebra space 3D, and that usually will give you a link to this page. And just the command for a space curve, because it's a 3D calculator, any curve is a space curve. So you just say curve, And then you have to give the X, Y, Z coordinates. So, and there's no vector notation. They just have you separate these by commas. So we did T over pi. I think there's a pi down here, comma. It was cos T, comma, sine T, like that. And then you have to tell it T is the variable and give limits on T. So if you go from 0 to, if you want 3 rotations, you got to go up to 6 pi. 6 pi there. And then it should just work. You can see it does hidden line removal for the part that's below the plane. Okay, so you see that? That's basically what I tried to draw by hand. It's pretty tough to do that convincingly. And of course it looks better. I don't like seeing that plane though. I'm gonna hide, I think you can hide the plane. There, now the plane is hidden. And you can spin it and just watch it go round and round. Okay, any questions about that thing? So you're gonna, I think the homework will probably ask you to do some 3D graphs and on a computer. And so feel free to use this. When they don't want you to use a computer, I think you should probably not, because you know, on the exam, you're going to be sort of in the position of having to figure out how to do this without any help from from GeoGebra. So just keep that in mind. It's there. It's super easy to use. Make a note of the syntax. If you just type the word curve, C-U-R-V-E, it gives the syntax. Okay, so it gives expression. That's 3-dimensional curve. Then the parameter variable, that's T, and then the start value and the end value for T. So X of T, Y of T, Z of T, T the variable from 0 to 6 pi. All right, so that's pretty useful. And I'm gonna go ahead and pop back over to my iPad. Any questions about that? And definitely hard to draw some of these things convincingly by hand. Definitely hard. Even a line is hard to draw, really. Okay, so we're going to get a little bit more to do. Y'all good?
Yep.
Yep. Okay. Fine. All right. So then, let's go. I'm supposed to do, and they have homework problems where they ask you to describe the intersection of 2 surfaces. So one moment while I look for it. There we go. Okay, so the intersection of 2 surfaces is a space curve. Okay, so for example, we want to find a vector function that gives the intersection of z equals 4x squared plus y squared and y equals x squared. Okay, you know, this first one we've talked about elliptic paraboloids. And this guy right here, because there's no z, that's a parabolic cylinder. If it's missing a variable, it's a cylinder. And I'm sort of reluctant to try to draw it, but I don't really need to. I'm going to give it a go here. So, so let's see. X goes out 2, Y goes out 1. It's going to be sort of like this, I think. I'm trying to draw my oval first. That may be a little less than good. Let me level it out a little. Okay, so, all right, and then okay, I'm gonna try and draw a parabola now. Like that. Ain't bad. I've seen worse. Okay, and then it says my z-axis, y equals x squared. I could almost, let me do a little more angle on that. I could almost just kind of imagine. I'll do this in gray, y equals x squared, a little kind of a parabola that goes this way. Okay, this surface here is the z equals 4x squared plus y squared. Like that. And then I'm sort of trying to kind of put these two things together. So what if I just sort of pictured this parabola? Oh God, I'm not gonna be able to do it. Okay, I'm trying to picture a parabola kind of doing this and then kind of going like that. That's just me projecting this parabola up onto the surface, but that's not a good picture. So I feel reluctant to keep it. It was a good try. How about we look at it in GeoGebra? So I'm going to go back to GeoGebra. Maybe I can delete what I got here. There, it vanishes. Okay, so now we're going to do y equals 4x squared plus y squared. I'm sorry, z equals, my bad, z equals 4x squared plus y squared. That's my elliptic paraboloid. Okay, I can change the color if I want. I think there's a way to click on that. Settings. The color just is just hideous to me. These are all pretty hideous. What about that? Ooh. Yeah, these are all hideous. Okay, so there's my paraboloid, elliptic paraboloid, and now I have to do the cylinder. So the cylinder is just y equals x squared. Okay, now you can see the intersection here going up where the green and the blue meet here. That's the space curve that we're trying to parameterize. And as I look at that, I'm feeling better about the picture I drew. Okay, so let me go back to my notes now. Okay, yeah, looks better all the time. Okay, so what you want to do is notice, first of all, that x is independent here. It's not mentioned. See, y and z are dependent. X is independent. So it can be anything it wants to be. So I'd say let x be t. Okay. Then you can see then y has to be x squared. Well, which is t squared, right? Y is x squared, but that would be t squared. Okay. And then z is 4x squared plus y squared, but this would be 4t squared plus t squared squared. Okay. So that's 4t squared plus t to the fourth. And so then I would write my space curve r of t with my x, which is just t, my y, which is t squared, and my z, which is 4t squared plus t to the fourth. Just like that. And you've traced out the curve. Now, if you really want to impress your friends, which I know you do, you can pop open GeoGebra and we can just say curve. What? Well, let's have x be t, y be t squared, oops, z to be 4t squared plus t to the fourth, and then have t go from -1 to 1. So I would say t comma -1 comma 1, say a little prayer maybe, and then I don't know if you can see it, but it's put a black curve on the intersection there. So that makes it a little more apparent. Can you guys see that? And then if I, maybe I'll go -2 to 2, just to stretch that out some. So it goes up a little higher there, right? And if I wanted, I could get rid of the red so that you could just see it on the paraboloid. Yeah, I feel pretty good about the picture I drew. Okay. Any questions about that? All right, back to the notes. Okay. Let's do some two-dimensional cases. Just a kind of a checklist here, vector curves in 2D. So the circle, I think I gave, but I'll give it again. Circle of radius A. So you do an r of t equals a cos t, a sine t. So this, you gotta have the same radius on x and y. And then the ellipse. Let's say the ellipse would be x squared over a squared plus y squared over b squared equals 1. So then you'd say r of t is going to be just like a circle, a cos t, but the y coordinate gets a different radius, b sine t. And if you let the first coordinate be x, and the second coordinate be y, you'll see that if you plug that into the equation for the ellipse, it's just the Pythagorean, it's just the Pythagorean identity, cosine squared plus sine squared, which always has to be 1. So it's definitely true. I almost don't want to talk about the hyperbolic curves, so I'm going to pass that. If you just have y equals f of x, any curve at all, then you would do x equals t, y would have to be f of t, right? So put them together and you got r of t equals t comma f of t. So basically all of our curves, whether in 2 or 3 dimensions, have got to be expressed as a vector function. Okay, I think that's it for that section. We're going to leave it behind. It's super simple, other than you're going to have, the hardest thing they do is they give you matching problems in the homework. So they say, okay, here's 3 functions, 3 vector equations, and here's 3 graphs, match them. So that's a challenging problem.